Good day to you. I'm John Kolak, the president of Precedence Corporation, and I'm going to be your instructor today for a seminar entitled Introduction to System Safety. Now, my background in system safety is multifaceted. I actually am a practitioner. I'm a certified safety professional, and I've used system safety techniques in everything from hazard assessment to accident investigation. I'm also a Department of Energy trained accident investigator and certified in system safety through the DOE. And I also taught system safety engineering actually at the collegiate level for a couple of years in the University of Wisconsin. Now, normally system safety would be a concept far too complicated to cover in a 45-minute seminar like this one. So as the name suggests, it will be introductory. We'll just give you the high points. But really, I have two goals with this. If you're a manager level person listening to this presentation, I want you to take note of the fact that we have much more precise ways of assessing risk in the workplace and determining hazard controls and predicting accidents than you may be aware of. So I'm going to want you to start requesting or requiring, especially things like accident investigations, to have a rigorous hazard assessment and hazard control process associated with it. If you're a safety professional or an engineer listening to this presentation, I want you to learn this material such that you can improve your skill set. And if you don't understand anything about system safety, to go get skilled up in that area, because as safety professionals, we owe that to the management teams we serve to be able to give them the best quality assessments we can. And system safety is absolutely the best at hazard assessment. Now, if you look at the pictures in the slide, it illustrates where systems came from. Back in the day, in the 40s and 50s, we used to use quality improvement was actually had, if you will, by what we call the fly, fix, fly procedure. Everybody remembers Chuck Yeager, who had the right stuff. If they were, for example, testing a new fighter jet out, Chuck or somebody like him would take the plane up, fly it out to its envelope of performance, and if the plane didn't break up and kill the pilot, he would land, narrate to the engineer what he learned, and then they would make changes and fly it again. So that's where the fly, fix, fly procedure came. Well, over time, the systems became so complex and so expensive, or the event, like for example, a nuclear meltdown would be unthinkable. We had to come up with a process to assess and control risk without having a single data point of actual data of a meltdown or a multi-million-dollar fighter jet crashing. So this is really where hazard assessment and control came from. It used to be called the fly, fix, fly procedure, and we changed that when the energy sources were either so severe or the cost of the items were so expensive that we no longer could afford to have a single loss. That's really where it came from. Now, some of the concepts we're going to talk about is the idea of safety as a system. We're going to talk about how this translates into hazard analysis. I'll give you a couple of high-level financial calculations just to illustrate for you how system safety can be used to much more precisely predict the costs and the benefits to the organization of using hazard control. And then finally, I'll leave you with a most powerful tool in all of safety called the Management Oversight and Risk Tree, also known as the MORT chart. So let's go to the next slide. Now, this is a very important concept that you see on this particular slide. The graphic on the right illustrates 8 major subject matter areas that all contribute to safety. These are the principal things we assess. These are the main subject matter areas that all contribute to the safety process. You'll see at the top of the food chain, leadership and commitment. This is the management function. This has been determined and derived to be the most important element in the safety process, is the management team that not only funds and supervises the process, but actually manages the safety process. At the bottom, at 6 o'clock, we see the proactive measures. This is hazard assessment and hazard control without having a loss. That is where the money is to be made in safety, anticipating and controlling hazards before they cause a loss. All the other elements listed are all very important, but they are sub-levels of leadership and proactive safety measures. Now, if you can visualize this graphic as being a mobile hanging from a child's crib, if you will, all of these elements are suspended and they all interrelate with each other, such that if you were to tap any one of those elements, bump into it, the entire mobile would move. This concept is true of systems as well. There's very few things you can do in your system where you change a process you do something that doesn't have a ripple effect to other processes. So your hazard assessment system is not just one directional, it is multi-directional. We are going to assess the impacts of system changes on the entire system, not just one particular subset of that system. Therefore, safety performance is a function of the interrelationships of these processes, not the quality of each of the processes themselves. It is better for you to have average quality elements that all interrelate well than to have a state-of-the-art maintenance program or a state-of-the-art training program and a dysfunctional management system, for example. We also want to point out that accidents have to be categorized or viewed as a catastrophic system failure. When you've had an accident, all of the things you see here have failed. The management systems, the maintenance processes, or whatever may have all contributed to this loss. We have had a catastrophic system failure. So this needs to be assessed with that level of urgency. And the idea of cosmetic versus system changes simply means that if you're going to make a change that's going to last, you're going to have to change it at the system level. You're not going to be able to do it by just changing the name of a safety process or glossing over the process. You're going to have to change one or some combination of these 8 elements that you see in the slide on the right in order to affect a change that will last. So let's go to the next slide. Let's talk about some key system safety concepts that are going to be relevant for the rest of the presentation. The first one is called life cycle management, also known as cradle to grave. Many of you already recognize this from the environmental or the process safety level. Life cycle management simply means that the hazards associated with any system vary by where you are in the life cycle. For example, implementing or installing a new piece of equipment. Of course, when you first put the system into production, of course, there are different kinds of hazards than when the system has been in functionality for many years and you're just maintaining it. And then, of course, when the piece of equipment nears its life cycle, when it's about ready to be demolished or retired, of course, there's different hazards with that as well. Your safety system needs to adapt to both where the humans are and where the equipment is in the life cycle. The idea that safety is a line management responsibility cannot be overstated its importance. Line management must manage safety like anything else. Safety is not run by the safety department. It is a function of management. And if your safety department does their job well, they will disappear. They will be behind the scenes feeding management the information they need to be able to implement an effective safety program. So it is a management function. It is top down. It does not bubble up from down below. The idea that safety is productive suggests that you can measure how expensive it is to manage safety, and you can actually manage too much in safety. So yes, we can in fact do financial calculations. We'll give you a few here in this presentation, but we can actually assess where the lines cross, if you will, where you get maximum benefit at the most optimal cost level in the process. So safety can be calculated and managed like any other part of the process. The idea that safety requires upstream effort, well, that means the further upstream in the process, the system life cycle, you can make changes, the better off you are. So if you can change something at the engineering level when it's just a concept, of course, that's far less expensive than retrofitting a piece of equipment that's already been installed. And the final point on this slide is safety depends on what was known as the safety precedence sequence. In system safety, you'll know that as the hierarchy of risk control. Let's go to the next slide. We'll talk about that. Now you can see in the picture of the NFPA 70 book, they've actually got what used to be known as the safety precedence sequence, now called the hierarchy of risk controls. This simply suggests that some of the things we do to reduce risk, some of it are more effective than others. So as you can see at the top of the food chain, risk elimination or an energy engineering control, these are all things we do to actually reduce the risk associated with a various process, meaning we don't have to give people protective equipment or train them to do this. It's inherently engineered into the process. So for example, an arc flash study is an example of an engineering control where we can actually lower the incident energy exposures by engineering controls. And if we do that, it's safe for anyone who works on it, regardless of whether they have the right PPE on or not. Providing barriers are just dead fronts in the electrical world. They put a barrier between people and the energy sources that could hurt them. Warning devices are like the backup alarms on forklifts. They let you know the hazards are there. Doesn't do much to actually improve the process. It just relies on you to get out of the way. And the lowest form of protection, as you can see, is controlling hazard with protective equipment, rules, and procedures. And of course, when we do that, we are going to have redundant systems to manage hazard probability. That is to say, we are going to overlap safety rules such that the likelihood that you're going to violate all those safety rules at the same time is as unlikely as an engineering control. And then if you don't do any of those things, you get what we call residual or residue risk. We accept whatever risk we don't manage. So that is actually a management concept. It's our legal reality that whatever risk you don't manage, you accept that risk, and some companies, as you'll see, accept too much risk. Let's go to the next slide. Okay, let's review a concept that many of you are already familiar with. That is the concept known as a risk assessment code. Now, we've already discussed that risk is actually a function of hazard severity and hazard probability. And on this matrix, you can see where they intersect is actually what's going to determine what we do about the hazard being evaluated. Now, again, it's important to understand the numbers I have affixed to this matrix are not hard and fast. It is actually a management decision as to how to fill out whether something is an unacceptable risk to management or an acceptable risk without intervention, and everything in between. Now, as you apply this, some of this is intuitive. For example, if you're in the top left corner of the chart, the matrix, if you were evaluating an energy source where you have catastrophic loss and it's happening a lot, you obviously wouldn't need a calculator to figure that out. You would intuitively manage it. It needs to be managed. The other end of the spectrum is also pretty obvious. For example, if you have an energy source that is extremely remote in its impact and it's very unlikely to happen, intuitively you would know that you really don't want to devote any resources to managing that particular hazard. What is interesting, though, when you use risk assessment codes is that when you do a formal assessment, you may find that processes you wouldn't expect float to the top as being the thing that needs to be managed in that particular system, because when you actually do a formal analysis, you may be surprised at what you learn from that process. So risk assessment codes are inherent to system safety, inherent to hazard assessments, and we'll use a variation of this when we do some financial calculations later in the presentation. Let's go to the next slide. Now, what's important about a risk assessment code is that you have well-defined, clearly defined operational definitions for both severity and probability. So we won't go through every one of these in the presentation, but under the severity umbrella, for example, we're going to define catastrophic loss as death, complete system loss, greater than $500,000 in losses, or incident energy values of 100 calories or more. So again, the actual definition I've given you here is not one that you have to use yourself. Just suffice it to say that we quantify each level of severity in terms of financial, system impacts, and human impacts. Probability is the number of negative outcomes versus a number of iterations. Some of these numbers we can get using our own data. For example, if you have a behavioral safety process in your company, you are gathering statistically significant sample sizes of human behavior. So it may be possible from your own experience in your own company to use these frequency numbers and the frequency definitions. Suffice it to say that, again, you can get this data from other places as well, but it is critically important with any risk assessment that we have well-defined definitions for severity and probability. Let's go to the next slide. Let's just take a look at a couple of financial calculations that are possible using the idea or the concepts we've discussed thus far. However, using some system safety-based tables instead of just straight risk assessment codes. There's two calculations we're primarily going to be using. One formulas we'll be using. One is called total risk exposure codes, known as TREC, and also total risk exposure. Again, just keep in mind that the science of these is built into the process, into the formulas, so you can trust the numbers that we're going to come up with because they've been derived using a very large data sample over many years. Let's go to the next slide. All right, let's take a look at the severity code matrix associated with the financial calculations we're going to be discussing here. Again, in the left column is the TREC code that we're actually going to be using for the table. The middle column is the range of losses associated with the accident in play or the loss in play. So again, this is the loaded loss. Okay, so we're not just using direct costs. You would be using the loaded costs of the event, whether it's an accident or an incident, and the range. And then the average is just useful for the formula, which we'll look at in just a second. So again, this is a severity code part, and it's only a financial calculation that we're talking about here. We're not including other things that were included in the risk assessment code, for example, the loss of human life associated with this. So this is just the financial calculation. So let's go to the next slide. Under the probability, once again, the TREC code we're interested in is in the left column. The range is the number of accidents we're going to have per the number of iterations. Okay, so again, the middle range is accident or incident data that you can either have directly from your own company or possibly from other consortiums or others that produce loss data. And then once again, the average is in scientific notation, just in the right column. That will become useful here again as we go to the matrix, which we'll show you now. So let's go to the next slide. So this is actually the TREC table, and as you can see, it is nothing more than a summing table where they intersect. For example, if I have a probability code of 6 and a severity code of 6, you notice where they meet is 12. It's simple enough. All we're talking about here is adding them together. So the TREC score will actually be the sum of the two elements, the probability element and the severity element. So let's go to the next slide and talk about how to use this. Again, we will not obviously go through all these calculations, but once you have that total risk exposure number, you can make a number of financial calculations from that, and it can be very useful for you to do a multi-perspective evaluation of the losses and the potential savings of your safety or risk management program. So again, each of these has financial implications that are beyond the scope of the presentation to go through each of them, but just suffice it to say there's a lot of horsepower we can get by just simply doing the calculation to get to a total risk exposure. Let's go to the next slide. Now, human errors, when we talk about human error rates, this is also very important because many of you are managing safety primarily using safety procedures and personal protective equipment. So, of course, human errors are not only significant in precipitating accidents, but of course the human error rates are based in the qualifications and the training and an oversight or supervision given to employees. So what we have here is a human error rate prediction table. This is not all inclusive. I just excerpted it for your use. But again, we know that various kinds of processes, like for example, if you look at the top line, a two-man crew with role reversals, meaning two of you are going over, for example, a switching sequence formed together, the likelihood of a miscue in that element is 1 in 10,000. So earlier we talked about being able to implement iterations or number of negative events in the total risk exposure code tables. This is one of the places where you could implement the human factors part of that. You'll also note that the credibility limit is 1 in 100,000. That is considered the best it's going to be when we talk about using humans to manage processes. That for every 100,000 iterations of a task, it is reasonable to expect you're going to have one negative outcome associated with that process. At the very bottom of the slide, an older program that used to be used for this is called THERP, or Technique of Human Error Rate Prediction. We've got better versions of this now, but suffice it to say that we can even predict human error rates, and that can be integrated into the hazard assessment process. And this is very valuable for you if you want to put more meat on the bone with respect to human factors. Let's go to the next slide. Now, of course, we will not have enough time to go over each of these hazard assessment tools. I did want to give you at least a brief overview of the number of tools and the kinds of tools that are available within system safety to help you. Again, there are 13 different types of hazard analysis tools within system safety, and we safety people would, of course, want to become fluent with all of them such that if we are doing a formal hazard analysis or an accident investigation or an incident investigation, that we're able to use the tool that gives us the best precision with respect to assessing risk and making the best choices we can on behalf of the organization. So this would certainly augment those of you that are using JSA or JHA as your primary hazard assessment tools. This is just more tools to add to your toolbox, if you will, and hopefully this will help you to do an even better job of assessing risk on a day-to-day basis. Let's go to the next slide. I'm going to use my remaining time with you to talk about the most effective safety management tool in all of safety, known as the Management Oversight and Risk Tree. The Management Oversight and Risk Tree is actually a picture of the safety system. It is a graphic interrelationship document or diagram of the safety system. So I said how to become the consummate safety consultant. It's meant to be tongue-in-cheek, but in reality what it means is if you follow the MORT chart, you will cover every single element in the safety system that needs to be evaluated in your own organization. And by the way, you don't have to have letters after your name to use the MORT chart. I've trained plant mechanics at a power plant to use the MORT chart, and they ate this thing up. You do not need to have a higher education to use it. It is a very, very intuitive tool once you understand how to use the chart. So let's go to the next slide and we'll jump in. So the basics, as I said, MORT is actually a picture of the safety system. It is a graphical representation of the entire system. Now the MORT chart is actually a fault tree, meaning we normally use it to evaluate faults in the system. And in this case, the fault we're talking about is an accident. It's normally used as an accident investigation tool. So if you have a bad accident or a near miss that could have been a fatality, you're going to want to do a MORT evaluation of that process. You will be able to evaluate every part of your system that needs evaluation. You can identify parts of the system that are defective or less than adequate, if you will, and then you can use the other hazard analysis tools and hazard control tools to manage the risk effectively. And that's the key part of this. We can actually measure whether we've got the system managed or not. So the definition of companies that are good at safety is they think they've managed safety well. The best-in-class companies in safety know they've managed safety because they've actually evaluated it, and MORT is a part of that. Now, MORT employs Boolean logic gates, and that sounds like a $10 word. What it simply means, those are what we call AND gates and OR gates. Just file that for a minute. I'll show you what that looks like in the next slide. What's important about the MORT chart is it actually connects base level events to the actual accident event itself. So, for example, whether you had a tailgate discussion that day or somebody showing up on the job under the influence of drugs, how did that interrelate? What did it affect that actually contributed to the accident? The MORT chart allows you to analyze things like that. So hopefully just by thinking about it, you can immediately see some value for that. But if you ruminate on that at all, that is an unbelievably powerful thing that most of us safety people are not able to do, to be able to connect something as basic as that, what was covered or not covered in a tailgate discussion, contributing to the loss that happened in that particular event. That's very powerful analysis. There's also something known as a mini MORT chart, and it's, as the name suggests, it's an abbreviated chart. If you get good at the entire chart, the mini MORT chart allows you to use it for more on-site or check-in evaluations, if you will, less systemic in their scope, yet using the power of the chart for the key items in the chart. So mini MORT is an option that you can get online. And there's also the MORT User's Manual. All of this, the MORT chart and the User's Manual, are federal documents. They are not copyrighted. You can use them as you so choose. So just go online and look up MORT, and they will give you the chart. So let me show you a picture of this, and then we'll close it out. Okay, what you see in front of you is the very top, or the initiating event, the source side of the MORT chart, if you will. Now you're going to notice there's a couple of logic gates there that I'll just quickly explain how they work. The first one you see underneath injuries or damage is called an OR gate, if you will. You notice it has a curved bottom on it. An OR gate means that in order for the event to happen above it, in this case injuries or damage, you got to have anything that's underneath the OR gate, in this case, oversights and omissions or assumed risks, either one of those could cause the injuries or damage. So the way to read this chart is if you had injuries or damage, you've either had an oversight or omission, or you've assumed too much risk, or both. Okay, so when you have an OR gate, anything that's underneath the OR gate could cause the event above the OR gate. Now, go down to the bottom of this, you'll see there's another graphic there, and it's called an AND gate. It has a straight bottom on it. Now, when you have an AND gate, it means that in order to have the event above it, you have to have everything underneath it. So the way to read this is, if you've had an oversight or omission, you have to have a specific control factor less than adequate, and you've had to have a management system failure less than adequate. So when you have an AND gate, you got to have whatever it is underneath it. If there were 20 items underneath that AND gate, they all would have to happen in order to have the event above it occur. So let's look at the chart again. Let's take a quick look at it, and it'll tell you some very powerful things. First of all, if you have an injury or a damage, you've either had an oversight or omission, or you've assumed risk. Assumed risk means there are things we just choose not to manage. So for example, we don't engineer systems to protect people against lightning strikes out on the parking lot of an office building. We don't do that because the chances of a lightning strike happening are so remote that we wouldn't even consider doing that. So we will just assume that kind of risk. Well, unfortunately, some customers that we have will assume too much risk. They will not manage things that they should, and they will just live hoping that nothing bad happens. That's called an assumed risk. Now, if you don't just do that, if you try to manage it, if something went wrong, you had an oversight or omission, let's go to the bottom of the chart and let's talk about two really important concepts. First of all, if you've had an oversight or omission in the system, you have to have both a control factor fail and a management system fail. Now you'll notice the lines that go from the AND gate to either side of this have different words, don't they? On the specific control factor side, it says what happened. So when you do MORT analysis, everything on the left side of the chart, the specific control factors, will answer the question, what happened in this situation? Everything on the right side of the chart will, under the management systems umbrella, will explain why it happened. Now, this is critically important for you managers especially. First of all, what it means is that if you've had an accident, you have at least two causal factors. There will never be an event that you have that doesn't have at least two causal factors, a what happened part of it and a why it happened part of it. Also, this also explains why, for example, we hold management accountable for the safety of the system. The why of an accident is always a management system failure. Now, if you're sitting and listening to this seminar and you're saying, well, wait a minute, what about acts of God here? What about things we can't see coming? Well, that has actually been derived in system safety. The chances of a non-system causal event, in other words, you have an event that is truly could not be foreseen as part of the system, it is 4% of the process. 96% of the time when you have a system loss, it is a function of something in the system rather than just one that you couldn't see, a true act of God, if you will. So there's a lot of power in the MORT chart, and this is just the top of the chart. Now, the one other thing I want to tell you before we go on to picture the MORT chart is how do you make this into a positive tree? In other words, instead of investigating an accident, how do we prevent an accident? And all you got to do with the MORT chart is reverse all the logic gates. So all the OR gates become AND gates, and all the AND gates become OR gates. And if you do that, you then turn this into a positive tree from a fault tree. And if you can imagine this, safety people, imagine what that would mean. If I manage this using this chart, I will have every base covered, and I have a way of assessing each individual step. And if you do that, you will have a best-in-class safety system. So that's just the science of the top of the MORT chart. Let's go to the next slide. We'll make your brain swim a little bit when you see the whole chart, but just take a look at it for now without getting caught up in the details. Let's go to the next slide. Now, the box that I have in red is what I just showed you. This is the top of the MORT chart encapsulated in the box in red. So as you can see, the MORT chart has, well, actually 1,500 items. If you used all of them together, including the subroutines involved, it is a large, very complex chart. And that is true because the safety system is complex. Many people try and reduce accident prevention to simply linear, the so-called chain of events, if you will, of accident prevention. Accident prevention and the system is actually a series of interrelated processes, which I think you can see just by looking at the chart itself. And by the way, every item on that chart can be identified. There's a labeling system with it. It's included in the user's manual, and every single item in this chart is defined in the MORT user's manual. So for now, I would just like you to know it exists. Safety people, get to know this puppy. It is really, really powerful for you. Managers, just understand that if you have a bad one, you're going to want to do a much more rigorous evaluation than typically is done in an accident investigation. And this would take, a week or so to do a full accident investigation using the MORT chart, but it is worth it because you will finally get to system contributors to accidents, and you will finally be able to know that you've managed the processes that are in play. Let's go to the next slide and we'll close this out. So some closing thoughts. As I said, system safety techniques are by far the most effective means of assessing and controlling hazards. No question. It's not even close. Nothing we have in the safety profession is close to this level of rigor and this level of science. System safety take a lot of subjectivity out of the safety management process because we can quantify things using data that has been proven to be so, especially with those financial calculations. It'll take some effort to learn how to use these tools, but it is worth it. You can get trained in this, not only from places like I do this training, but of course many different places do it as well. And it is well worth it to send your people to this level of training, and you don't need to do it alone. And toward that end, as we always do with Grace Engineering, if you're interested in implementing this, you can kind of get a hold of me offline at no charge to you, and I will help you to get yourself set up going down the path of using MORT. Okay, so with that, I'll turn it back over to Banu, and we'll field your questions, and hopefully this has been helpful to you. God bless.
Grace's PESDs consist of voltage indicators, voltage portals, and combination units of the two. Our voltage indicators visually represent the presence of voltage with flashing or non-flashing redundant LED lights. In addition, these indicators also show the lost phase, stuck blade condition, and dissipated energy of the connected source. The voltage portals offer the maintenance personnel with a no-touch voltage detection using an NCVD pen on the outside of a grounded electrical cabinet. On the other hand, a safe test point portal with 102 kiloohms high impedance protected circuit offers the qualified person to perform the absence of voltage test from outside the cabinet without opening the door. These high impedance protected Cat 3 and Cat 4 rated and UL listed PESDs provide the means to safely verify presence or absence of voltage, either phase to phase or phase to ground in both AC and DC systems up to 1000 volts, without exposing the worker to arc flash or shock hazards. When properly incorporated into a facility's electrical and mechanical lockout-tagout procedure, PESDs enhance the compliance with NFPA 70E, CSA Z462, and OSHA energy isolation principles. All of our PESDs can be combined in several available standard and custom configurations for either door or flange mount installations, as well as with procedure labels to further reduce the task risks to bare minimal levels. Voltage Test Station is another form of PESD that combines a voltage indicator and safe test points in UL-recognized lockable housings with Type 4, 4X, and 12 ratings. Other PESD product variations include flex mount voltage indicators that can mount onto any electrical enclosure with 3/4 inch or M20 conduit knockout, a fiber optic voltage indicator for use in dead front bus panels with no voltage to the door, and a medium voltage indicator that can bolt directly to the bus bars from 2 kV through 43 kV systems. No matter how simple or complex your lockout-tagout procedure is, we have a PESD that answers your unique need. Over a decade, we have earned the trust of many Fortune 500 companies that have installed hundreds of thousands of these PESDs into their equipment as part of their electrical safety programs, and are a testament to our product reliability and effectivity. Visit www.pesd.com to understand the benefits beyond compliance.